In this video, I'm going to discuss about concept of entropy. Okay, here I'm going to consider PV diagram, that is pressure volume diagram, and in this diagram I'm going to consider three isothermal processes which is at temperature T1, T2 and T3. Here I'm going to draw, this is the first isothermal process. I'm going to represent it by T1, which is at temperature T1, and this is the second isothermal process which is at temperature T2, and this is the third isothermal processes which is at temperature T3. Here in isothermal process, temperature remains same, but there is change in pressure and volume of the system. And also here I am going to consider two adiabatic processes, that is, here I am going to draw, this is the first adiabatic process and this is the second adiabatic process, and I am going to denote these adiabatic processes by L and L. And also let us denote these points. I am going to denote this point by A, it is B, C, D, and this point by E, F. Here you can see that A, B, C, D, it forms an Carnot cycle. We have already studied Carnot cycle and Carnot engine in last video, and here this is the Carnot cycle A, B, C, D, and C, D, E, F is also another Carnot cycle. Here the first Carnot cycle is working between the temperature T1 and T2, that is here the first Carnot cycle, that is A, B, C, D, which is working at temperature T1 and T2, and similarly D, E, C, F, that is D, C, E, F represents the another Carnot cycle which is working at temperature T2 and T3. Okay, we have already studied about the Carnot cycle. Here now I am going to consider the first Carnot cycle, that is A, B, C, D. Here I am going to consider the first Carnot cycle A, B, C, D. Here Q1 be the amount of heat added to the system or added to the engine, and Q2 be the amount of heat rejected by the system. And we know that from Carnot's engine, efficiency is given by in Carnot's engine T1, that is the temperature which is at higher temperature, and minus T2 which is at lower temperature, and T1 the higher temperature. This is the efficiency of the Carnot's engine in Carnot cycle. And also we know that the efficiency relation, that is eta is equals to Q1 minus Q2 divided by Q1, that is Q1 is the amount of heat added to the system, Q2 is the amount of rejected by the system, and Q1 is the amount of heat added to the system. And from these two efficiency equation we can write T1 minus T2 divided by T1, which is equals to Q1 minus Q2 divided by Q1, or we can write here 1, that is T1 divided by T1 is equals to 1 minus T2 divided by T1, which is equals to 1 minus Q2 divided by Q1. Here if you interchange these two terms, here 1 and 1 going to 1 get cancel each other, then we are left with Q2 divided by Q1 is equals to T2 divided by T1. Here minus minus gets cancelled each other, or we can write it as a, here I am going to interchange the terms, it becomes Q1 divided by Q2, Q1 divided by T1, which is equals to Q2 divided by T2. And let us denote this equation by 1. And also similarly here another Carnot cycle is formed, that is CDEF is the another Carnot cycle. Here the amount of heat absorbed at temperature T2 is Q2 and the amount of heat rejected by the system which is at temperature T3. And again from above equation we can write the efficiency. We can write the efficiency equations are Q2 divided by T2, which is equals to Q3 divided by T3. And let us denote this equation by 2. And here comparing these two equations, that is 1 and 2, comparing 1 and 2, we can write here Q1 divided by T1 is equals to Q2 divided by T2, or from this equation we can write here Q2 divided by T2 is equals to Q3 divided by T3, Q3 divided by T3. And if you consider number of isothermal processes, then Q3 divided by T3 is equals to Q4 divided by Q4, so on, which is a constant value. And here in general we can write this equation as a, that is, if let us suppose if we consider Q is the amount of heat either absorbed or rejected at temperature T while going from the adiabatics L to M. Here we can write this equation as a Q divided by T, which is equals to constant. Or here if the adiabatics are too close, that is this L and M are very close to each other, then we are going to consider dQ is the quantity of heat absorbed or rejected at temperature T. Instead of Q, we are going to consider the small amount of heat is absorbed is dQ, which is at temperature T. And here I am going to write it as ds is equals to dq divided by T. Here ds represents the change in entropy, that is this ratio is known as a change in entropy between two adiabatic states, that is dq by T gives the change in entropy between two adiabatics L and M. Here let us suppose I am going to consider S1 be the entropy of adiabatic L and S2 be the entropy of adiabatic M. Here let us write change in entropy for these two adiabatics, that is I am going to write change in adiabatic. Here I am going to take S2 minus S1, it gives the change in entropy which is equals to, it is passing from L to M, so I am going to integrate this equation. So this equation becomes integration of L to M to dq divided by T, and this equation gives the change in entropy between two adiabatics L and M, which is equals to integral of L to M dq by dt. Here since in adiabatic processes there is no amount of heat is added to the system or there is no amount of heat rejected by the system, so here dq is equals to 0, that is the small amount of heat absorbed or rejected is 0. So we can write this equation as a, if dq becomes 0 then S2 minus S1 is equals to 0, that is change in entropy value is 0, which means it indicates that during an adiabatic changes there is no change in entropy.